Hello. Now at the outset, let us look at the energies that we are dealing with. So I'm going to talk a little bit about the electromagnetic spectrum. So you see the electromagnetic spectrum, uh, it has got this variety of colors, and you are now going from, for example, in terms of energies, you're going from in the infrared, for example, to let's say X-ray. You're looking at energies of 0.01 eV electron volts all the way to about hundreds or even higher, hundreds of electron volts. And the visible range is what we are largely interested when we talk about lasers. But then the lasers exist all the way from infrared all the way to UV. So the visible range is about 2.5 electron volts and centered around there. We should be able to quickly convert between wavelength, frequency, between bandwidths in nanometers, let's say, to bandwidths in hertz. So these are the kind of conversions we should know. So as you know that the wavelength and the frequency get related through the speed at which the electromagnetic radiation is propagating. So what we have is C is nu times lambda. So if you want to convert now delta lambda to delta nu, all that one needs to do is to rewrite this equation in the differential form. That is, I can write down my nu as C over lambda, and then I take I differentiate nu with respect to lambda. So what I get is delta nu by delta lambda. It just happens to be C by lambda square with a minus sign. So here lambda is the lambda average or the central lambda. Similarly, nu here is the nu average between the two. Now this is indeed true in this regime, but of course if you would like to, if you have lambda 1 and lambda 2 are reasonably far away, then you see what you need to do is you need to do delta nu. You can define as nu 2 minus nu 1, which by the way is C by lambda 2 minus C by lambda 1. Appropriate conversion between delta lambdas and delta nus. So this is the way to operationally deal with it. This is a very important aspect of laser. So in lasers, we will see that lasers are reasonably, the radiation coming out of laser is reasonably unaffected by the thermal noise which is surrounding us. That is, if I'm looking at a temperature which is roughly about the room temperature of 300 Kelvin, then if I'm looking at the typical energy associated with that, this you should remember is as 1 over 40th of an electron volt. So remember that we are looking at energy in the visible, which is associated with about 2.5 electron volts in comparison to the thermal noise, which is just 0.025 eV. So you see there is 2 orders of magnitude difference between the thermal radiation and the optical radiation, and this is what ensures that thermal excitations themselves play a very small role in the physics of all lasers. But of course, the materials which are using as active media, their characteristics do change with heat, and that has to be managed. But in principle, the experiments which are done with laser in visible range are certainly much more cleaner in terms of thermal noise in comparison to other experiments which are done usually in condensed matter, for example, where which are electronic measurements, for example, without using the lasers. These will be extremely susceptible to thermal noise. So that is the beauty and the sort of the power of lasers, and using visible light as a probe to understand phenomena. In the next part, I'm going to deal with basically the various aspects of lasers. As I said, we are looking at issues like directionality of the laser, the monochromaticity of the laser. With monochromaticity, I'll also invoke notions of coherence, look at coherence length and coherence time, and then we'll combine all this into a single quantity, okay, which kind of tells you the large difference that we have between a thermal source of light in comparison to a laser source. So let us now look at the directionality that we associate with a laser beam. So if you compare this with a thermal source, for example, any tube light or a torch, you would see that indeed that the radiation is emitted by the source in sort of a wide angle, whereas it appears as though uh, the light coming out of a laser is extremely pointed and remains more or less parallel. So the point is it really parallel? But you will quickly realize that moment you have a wave, which is the electromagnetic wave, a finite wave would always suffer from diffraction. That is, the solid angle that laser makes as the light comes out of, for example, so this is my cavity, and one of the mirrors is such that its reflectivity is less than 1, and this one is, let's say, close to 1. So you have the laser light bouncing back and through inside the cavity of the laser, but then you see that the light is coming out, and I'm just exaggerating. So you see that there is a sense of angular size. There's a finite angle with which the light actually comes out. So in a plane, this angle is delta theta. And then, so if you look at a solid angle, which is kind of a conical output that you're getting with, that solid angle actually goes like lambda square by A, where A is the area of the mirror through which the light is coming out. It's the area of that aperture through which light is coming out. So you see that, and you would know that delta theta square is delta omega for small angles, for small delta theta. So let us put some numbers to this. So for example, let us say that so let's put some numbers to this. So for example, in the visible, I'm taking lambda to be about 500 nanometers, right? So all the way the visible light is from 400 nanometers to about 650, 700 nanometers. So that is the range. And let's look at one of the somewhere on an average of 500 nanometers. And then let us say that my area is roughly about 1 millimeter square, right? That's a kind of thin pencil-like beam that you're getting. So my delta omega, which is the solid angle, so the solid angle is measured in sterdian. This would go like 5 into 10 to the power of minus 7 whole square, right? This is in meter square, and then you have 10 to the power minus 3 millimeter whole square, meter square. So you see that roughly this will come out to be about 10 power of minus 8 sterdian. So you see, that is, if I'm looking at delta theta, the kind of angle that I can measure for laser light will be about 10 power minus 4 of a radian. So that indeed is extremely small number. So that is why it appears to us that the laser light remains more or less parallel. The radiation is limited within this small angle, and that is what actually is responsible for extremely large brightness that we associated with a laser light. In the sense that if I'm looking at a 40-watt bulb, I don't have to worry about the dangers that might cause to my eye. But if I'm looking at even a 1 milliwatt laser directly falling on the retina, that can cause sufficient damage. And this is precisely why with the notions of brightness would come in. We will calculate this later, but then let us now look at the other aspect, which is monochromaticity. So the bandwidth that we associate with a laser, delta nu, is typically very, very small. What one sees is an extremely narrow band, a single pure color light that comes out of a laser. So typically, if you look at a thermal source, you see that your delta nu, this is, I'm looking at power as a function of frequency, and this, let's say, is associated with typical temperature. So this bell-shaped curve is what is associated with, for example, thermal sources at thermal equilibrium. This is the kind of uh, radiation curve that you would have, or also known as the black body radiation curve. So you see that this delta nu that we associate with, for example, sunlight, which is the surface temperature is around 6000 Kelvin. So this delta nu, the width of it is roughly of the order of 10 to the power of 14 hertz, which is precisely also the peak frequency that we associate with this thermal radiation. This is thermal light. In contrast, we have laser sources where delta nu can be extremely small. For example, helium neon laser in your lab that you would use for experiments would have is about few megahertz or even tens of megahertz. But you can have delta nu all the way to 1 hertz. You understand what that accuracy means? It means in 10 to the power of 14 hertz, I am sure that in 1 second, I am not counting 10 to the power of 14 plus 10. I'm counting 10 to the power of 14 plus 1. That is the kind of accuracy or the quality factor. So one associates a quality factor, which is a measure of this sharpness or the spectral purity. So this is captured by the ratio nu by delta nu. And you see that for optical wavelengths, for example, I have got nu of about 10 to the power of 14 hertz, and I have delta nu, let's say about even hundreds of hertz, right? This will give me about 10 to the power of 12. You see that such large numbers for the quality factor are unheard of in other mechanical or any other resonance systems, and in optical cavities and coming out of a laser, one can really have this quality factors to be extremely large. So a point to note that this large monochromaticity is because of the high quality cavity which is used to confine the radiation. It's this cavity that enforces this extremely narrow line width to the laser, and we'll of course come back to that as we go ahead.